YouTube can only host 15 minutes of my video, so I have to make a new one every 15 minutes. It wants my money. It wants me to pay for a professional service. Anyways, part two. Continue. Alright, so one of these quantities is not necessary when we are looking for acceleration using the changing motion equations. You guys know what it is? Yeah, we don't need mass right now. We'll need mass later. Okay, so right now you're looking for an equation that has acceleration, v final, delta x, and v initial. And you don't have to memorize it, but I'm lazy, so I memorized it. You can go equation hunting. You're looking for the equation with all four of those things. Emma. Wait. A equals to VF minus VI divided by where's my time? Okay, that doesn't work, does it? Because we don't have the time. Yeah. So there is another one that involves those four things. It doesn't have time in it. That's a big hint. Another big hint, it has some squares in it. See it? It's got a few squares in there. Okay, so V final squared is equal to V initial squared. Okay. This is the one that you use to find acceleration when you do not have the time. Ironic, I know. Okay, now this is a little bit of extra credit, but I'm gonna solve for acceleration without numbers. When you have too many terms, too many groups like this, it's best to eliminate any zeros. Do you recognize any of those groups having a zero in it? Yeah, it's this one. Okay, get rid of it. And for convenience, I'm going to go ahead and flip the equation to make it 2a times delta x equal to vf squared. Okay, and then we're isolating for acceleration, so divide both sides by 2 times delta x. Remember, delta x is just one quantity. Okay, it's just one symbol. Okay, so we've isolated our acceleration. We can substitute and solve. So if you substitute the correct values for VF, square it divided by 2 times delta x, you should end up with the solution of 1.47 meters per second squared. Right? You know, let's just plug it in just to be safe. 97 squared divided by 2 times 3200. Okay, the next part is so easy that it's insulting. How do you find the second unknown, which is the net force? Now, I'm going to write it the way that the equation chart has it, which is sigma F. Okay, and that's read net force is equals to ma. And that's it. You just plug in. Now you plug in the mass. Now you plug in the acceleration. Substitute and solve. Okay. All three problems can be solved this way. The only variation is which equation do I use to find the acceleration? And the answer to that question is, what givens do you have? Alright, let's go to the next contestant. Alright, who's got next? Who's got next? Stephanie. Elevator question. Okay. There are only 3.5 scenarios that we have to be aware of. Technically 4, but not quite. Okay. So the elevator is either at rest, or it has, let me just, okay, both, these have the same diagrams. When the elevator is at rest or traveling at a constant velocity, how does Fn compare to Fg? They should be equal. Right? So we say that Fn is equals to Fg, which makes you feel the same weight. Right? You feel the same weight because normally your weight is Fg. Okay, so when do you feel heavier? Heaver. When do you feel heaver? I want a better word than going up. When you're accelerating, when your acceleration is positive or up. Okay? So that means your FBD is going to have a normal force that is larger than the force of gravity. Yeah. Fn is what you feel. Fn is your apparent weight. So if Fn is larger, you feel heavier than normal. And you get. We probably don't have to. We don't have to work this one out. But you're looking for Fn to be smaller than Fg. What the heck? Let's go ahead and do the FBD. Alright, so FBD, we've done a lot of FBD this unit, so expect a whole lot of FBDs. It's many, yeah. So you definitely have to know these four forces when they apply. You're going to have to be able to draw the FVDs also and label the forces. But yeah, there are only a few forces, and it's just gravity, normal, and friction. Not really a big deal. Okay, so which one do you want to start with, Steph? So you want to do 4? Okay, the car brakes and slows down. Okay, first I'll do this on a flat surface. So that's my car. I don't want to be fancy. It's test time. I just want to be efficient. Okay, so number 4 says the car brakes and slows down. Okay. Let's say my car is moving to the right. Forces acting on my car should be force of gravity, normal, and since I'm moving to the right, if I want to slow down, I should apply a force to the left. Okay, and that's my force of friction. Yeah. Okay, so let me label this car on flat road. Okay. The reason why I want to do this is because I want to show an example of what happens if your car isn't on a flat surface. Let's say it's on an incline. And to make matter worse, let's say your car is actually a hill in San Francisco. Ladies. Okay, so what does this FVD look like? Okay, start with FG. What does FG look like? FG is still straight down. Okay, what does FN look like? The normal force has to be not parallel but perpendicular to the surface. Okay, so notice how Fn is slanted to adapt to the hill. Okay. FG is actually a little bit longer than Fn, and so what FG does is it's going to pull your car down the incline. So your car is going to want to roll down the hill. So what keeps it in place? Gravity wants to pull it down the hill. It wants to kill you. It wants to destroy stuff. So what keeps your car on the hill? Friction. Okay. Friction can help you slow down your car. It can help keep your car at rest. Okay. Friction also opposes your motion whenever it can.